So, good evening, everyone. So, we are back to the lectures in this course on the fundamentals of attosecond science and technology. So, in today's lecture, we will basically cover the remaining section on the nonlinear optics in a nutshell module. Once again, our references are pretty much the same, with the key here being particularly reference to the book Nonlinear Optics by Boyd. I am also grateful to Professor Trebino for his inputs and materials. Okay, so we have had quite some details discussed about the physical origin of the refractive index, optical nonlinearity, and we also discussed, as we began discussing, the energy momentum conservation in the case of nonlinear effects and so on. So, in today's class we will essentially extend that and conclude the section on conclude the section with a discussion on phase matching. Okay, so a quick recap about the fact that we are working on optical light pulses whose electric fields can be chirped, and we also understand how to deduce from very first principles the wave equation and propagative phenomena in optics with and without source terms. Earlier we did not focus on any source term whatsoever, but in lectures later on we did exactly that. We wanted to remain in a regime where we did not have any free sources of charge or current. However, we wanted to nonetheless include a scenario where through the constitutive relations, which is which for the electric field case is d is epsilon naught E plus P, and for the magnetic field it is B is equal to mu naught H by M. We essentially include material response through these two constitutive relations, but we are not considering magnetic media in this course explicitly until we may possibly mention it. So, therefore, magnetic media are also out of the equation, and we have then the case where the polarization, which is the response of the medium, essentially needs to be figured out when the medium is incident with an oscillating electric field E, right. So, we expand the polarization vector, which is essentially the density of local density of dipoles in the medium, using electric susceptibilities, the chi's of various orders. The linear optic phenomena are all captured in essentially the first order chi, which is chi 1. So, note the fact that we have superscripted this with 1 in the parenthesis, and subsequently we have the higher orders of chi, which is chi 2, chi 3. These essentially designate nonlinear processes, which we are particularly interested in this lecture and even hereafter. So, writing the equations down for non-magnetic media, we essentially get the two Gauss laws, then we have Faraday's law, and in the last equation containing curl B, we have this important term where the polarization response of the medium gets included. So, this leads us to something where the induced polarization acts as a source term for the otherwise propagating wave, and it creates in some sense the material response as we would want to determine this. We also looked at atomic response to in terms of the Lorentz oscillator model, and figured that the atomic response, which underlies how P responds to incident frequencies omega about resonant frequencies or natural frequencies in the medium omega naught, to be functions of this kind, and this essentially is from where chi originates. And we did a few substitutions and realized that the absorption coefficient and refractive index of these media are essentially a consequence of chi being complex in general. The imaginary part of chi is responsible for absorptive phenomena and the real part of chi is responsible for refractive phenomena. Now, the complex refractive index in itself can be plotted as a function of frequency omega, the driver frequency, with omega naught, the resonant frequency of the medium, playing a central role, where the refractive index has this Z shaped curve, all right, whereas the absorption coefficient is an even function of omega centered at omega naught. Okay. So, that is the equation for the transmitted field. Now, we also saw that essentially there are, as a consequence of the way in which the real part of the refractive index varies with frequency, we have regions where the refractive index increases with frequency, where dispersion is said to be normal, and in regions where the refractive index drops with frequency, dispersion is said to be anomalous. Now, all this yields itself into a picture where a light wave in a medium undergoes two kinds of effects. One is one owing to absorption and exponential attenuation as a function of length, and in the other it is essentially a modification of the phase, which in this case manifests through a modification of the effective refractive effective wavelength that the light wave has in the medium. So, the wavelength of the light wave in the medium is lambda naught, the wavelength in vacuum, divided by the refractive index n. This is the real part of the refractive index n, and the real part of the refractive index is again related to the real part of the electric susceptibility, which in an approximate expression is 1 plus a half the real part of the electric susceptibility. So, this is the primer underneath which underneath all nonlinear phenomena. This is what we discussed so far underlies all linear phenomena or linear optic phenomena, but we are interested in this course here and hereafter in nonlinear phenomena. So, what is about nonlinear phenomena? So, the nonlinearity arises from the need, if you wish, to consider terms in expanding the polarization as a function of electric field beyond the linear term, that is beyond the term where P is linear in E. That a power series expansion, the Taylor expansion, will lead us to a quadratic dependence, a cubic dependence, and so on, which is mediated through the chi's of second order, third order, and even higher order phenomena. So, we looked at the fact that the second order chi, which we are going to discuss out in detail, is responsible as a consequence of our writing the real electric field script, which is denoted here by script E, in terms of E times exponent of I omega t plus the complex conjugate. This makes everything real, and note this is a proportionality sign, it is not equality. So, there are some factors that we need to put inside on the right hand side to make them equal. Nonetheless, if I now consider the E square dependence of the polarization on the electric field, it is evident that squaring these two terms, this entire expression on the right hand side reveals a term where the oscillation happens at frequencies twice the initial driver frequency. So, you get the second harmonic, both E square and E star square, that is the amplitude of the complex conjugate term. So, these two are responsible for giving out the second harmonic. Again, realize that E square as a function, E square of t is also a real quantity. There is also this term which we may not have obviously foreseen, easily foreseen, which is a DC term. Okay, there is also a DC field created in the medium. So, all this is responsible for second order nonlinear effects. We can now take that polarization term and stick it onto the right hand side of Maxwell's equations, the inhomogeneous wave equation as we have called it. This gives rise to the a wave propagating not only at omega, but if we consider the nonlinear terms even at multiples of omega. This is what we saw. So, the secret of nonlinear optics, so to say, if there is any, is these mixing terms where waves tend to get mixed, and in the second order mixing we evidently get we evidently obtain terms where from an initial omega 1 or omega 2, in the case of two beams being present, we get the second harmonics for omega 1, which is twice omega 1, and second harmonics for omega 2 twice omega 2. Not only that, we also have cross terms in the quadratic expansion. So, we get omega 1 plus omega 2, which we particularly call sum frequency generation. When the two beams interacting in the medium, mixing in the medium to be specific, are not composed of identical frequencies, we can get as a consequence of doing the cross terms, we get an omega 1 plus omega 2 term when we multiply the term containing E and E, and omega 1 minus omega 2 when we do the product of terms containing E 1 and E 2 star, right. And we of course get two DC terms. So, rectification also happens in the medium, and it does give rise to a measurable field. Okay, so now second harmonic generation can be viewed as the absorption of two photons simultaneously by one atomic center, and the fact that this absorption need not be resonant, that is to say that the excited level into which the system gets excited here is need not be a real state, it can be a so called virtual state, which is extremely short lived, and from here the system can decay back to its original initial state or ground state, as we may want to call it, by emitting a single photon of twice the frequency and thus obeying energy conversion. The coefficient of two photon absorption is measured in Goppert-Meyers, named after Maria Goppert-Meyer. We also looked at the definition for photon density and so on, and the example of the very first demonstration of second harmonic generation by Peter Franken, and also the fact that there was some editorial cleanup of true data and so on. But then we took a fairly complicated scenario where we essentially took a fifth order process where we have the chi in question here is chi 5, and we have 5 fields where there are 4 incident fields E 1, E 2, E 3, E 4 and equivalently E 4 star, and the signal is the field E 5. So, this is a 5 wave or this is a 6 wave mixing process. In fact, this is also a causal field E 5, and omega signal is born out of a 6 wave mixing process where the 5 incident waves play a causal role and the 6th wave is essentially emitted as a consequence, but that is also present in the medium and it interacts with the causal frequencies from omega 1 to omega 5, and hence it is called a 6 wave process. Now, not only in the case of SHG do we have the prerogative to conserve energy, we should also conserve momentum in every physical process, right. So, energy momentum conservation must be simultaneously done, and as a consequence of what we considered in our earlier discussions, we have so far looked at, in the case of second harmonic generation, the fact that the two omegas of interest here combine as omega 1 plus omega 2 to result in a signal omega signal, okay, so that the omegas add up to give twice omega 1. Whereas, in reality momenta also should be conserved, and since momenta are associated with the k vector, in as much as omega 1 and omega 1 should add up to give twice omega 1, the momenta of the very same beams or photons should also add up to give the resultant linear momentum to the beam which is our signal, that is the beam propagating with a temporal frequency of omega signal. But then the question arises, well, we took it for granted that the two waves can mix and produce a 2 omega 1 beam. So, does that imply that in all conditions momentum conservation is also something that comes about as a byproduct, or do we get it for free? Let us consider the case where in a medium we have the two beams participating in the second harmonic generation process to have parallel k vectors, they are parallelly propagating beams, in which case if we add k 1 and k 1 to produce k signal, and simple rules of vector addition imply that k signal, which is k 1 plus k 1, should also be parallel to each of the k 1s, which anyway were parallel to each other. Now, the magnitude of the vector k 1 is omega by c naught multiplied by n at the frequency omega, it is n omega by c naught, right. So, now if this is the magnitude of each of the vectors with a moment with a propagation vector k 1, then since k 1, both the k 1s are parallel to k signal, we can write these equations in terms of the magnitudes of these two vectors. The magnitude of the first vector at k 1 is omega 1 divided by c naught multiplied by n times omega 1. There is another contribution from the second vector. So, on the left hand side, take considering the magnitudes, since the directions are parallel for all the three vectors. On the left hand side, we get twice omega 1, okay, divided by c naught times n at omega 1. Note the fact that this n is measured or determined at omega 1, whereas on the right hand side, do the same for k signal. K signal is omega signal divided by c naught multiplied by n at the signal frequency omega signal. Okay. So, therefore, on the right hand side we have twice omega 1 divided by a c naught multiplied by n, the refractive index at omega 1, right. So, as a consequence, now we look at this expression and take do all the simplifications we can. We cancel out the two prefactors of twice omega 1 divided by c naught. We are left with the fact that in order to conserve momentum simultaneously, we need the refractive indices, that is the refractive index of the pump beam at omega 1, the beams which cause the second harmonic, and the refractive index of the medium at the signal frequency, which is twice omega 1, to be equal. But omega signal is twice omega 1. So, can these two be equal in any medium at all? Is that possible? This is the question we were left with in the earlier discussion. This condition to be achieved is called the phase matching condition. Okay. We are asking for the phases to be matched for this process of converting the frequency from where the frequency of light is converted from omega to twice omega, or here omega 1 to twice omega 1. Unless this happens, unless the momentum conservation happens, we will never see a beam with a frequency at twice omega 1, because nature will not allow that violation, right. So, does this happen? Can this happen? That is the question we are left with. Does phase matching or momentum conservation take place? So, this is the big question. Will we ever have this process happening, or were we considering just some theoretical possibility, right? So, we want to look at that. What is the whole problem? If we consider any medium, we just saw a little while ago that for normally dispersive media, n depends on frequency, and as frequency increases, refractive index increases monotonically, right. This is an upward going curve. Now, this is, but in some sense we considered a very primitive atomic response and obtained this result. So, while we can argue that maybe there are media where the refractive index is flat from omega to 2 omega, which one may have to engineer. Since we did not assume any very special properties, all we took was a simple elementary atomic dipole and obtained this result for various media. This must be the most general too. So, in the most general case, we will not be able to phase match and basically get to the phase matching condition where which is n of omega is equal to n of 2 omega unless we do something special, or with just this simple scenario where the two incident cases were parallel to each other, K1 and K1 were parallel to each other. See here, in this scenario, the incident waves had propagation vectors parallel to, the incident waves had propagation vectors parallel to each other, and the signal, the propagation vector of the signal also was parallel to this, right. But the fact that these two are parallel to each other is something I want to stress. This was one of the conditions which we employed to deduce the result that the phase matching condition is n of omega should be equal to n of 2 omega. So, apparently this is never going to happen in normally dispersive media. What about anomalously dispersive media? If we had considered anomalously dispersive media, do they offer an alternative or a solution? We would have essentially had a scenario where the refractive index dependence on frequency would have been such. Okay. So, once again, n of omega and n of 2 omega being equal would neither in the case of normally dispersive media nor in the case of anomalously dispersive media be possible in the scenario we consider, where the beam with frequency omega 1 and the beam at frequency omega 1 with k vectors parallel to each other are parallel to each other, and these two beams are being made to interact in a medium with susceptibility chi 2, okay, second order susceptibility of chi 2. Okay. So, another fine point we should write, chi 2 also has a dispersion, it has a frequency dependence. So, since we are talking about the second harmonic generation process here, we must write chi 2, okay, in a sort of proper way, if you wish, where we basically write the two involved frequencies. In this case, they are both omega 1, they could well have been omega 1 and omega 2, and the resultant frequency at twice omega 1. So, chi 2 is frequency dependent, and this particular value needs to be picked for this for this implementation. It is a matter of detail, but since we are looking into details a bit more now, I should mention it. But the take home point or message is that all the three Ks, K1, K2, K3 are all parallel to each other, and in this case it seems we would not be able to achieve the phase matching condition, which is n at omega. We can also write it like this, it is done so in some parts of literature, or put a parenthesis around it. Whichever way you write, we are never going to be able to achieve this condition if K1 and K1, both the Ks of the incident pump beams creating the second harmonic are parallel to each other. So, what is the solution? Yes, Aditya. Chi 2 should be dependent on frequency too.
By definition, it should be a as a frequency dependent, it means you have some third order nonlinearity.
Only if it is dependent on the field amplitude. Chi 2 will have a dispersion. Chi 1 had a dispersion which looked, the dispersion of chi 1 looked like that about an omega naught, right. That is the real part of chi 1. So, likewise you are going to, real is already enough. So, likewise you are going to have a frequency dependence of the real part of chi2 as well. You also have the real imaginary part of, anyway, the green would be the imaginary part of chi1. So, again the dispersion of chi2 also is going to be kind of Lorentz, it is going to also follow some kind of a Lorentz structure, of course. So, therefore, here there is also a resonance. So, likewise the imaginary part of chi2 will also have a resonance. Well, the reason why, yeah, so now the point being that this is where we must appreciate the fact that we have in its full glory when chi2 is written, chi2 also depends upon the particular directions of polarizations of the two beams, that is the beam we index with I and the beam we index with J, the two participating beams. So, we are actually going to look at this in some detail in the next step. So, the point is nonetheless, that is a good question, Aditya. So, the point nonetheless is, can we ever achieve the so called phase matching condition? Okay, this seems to be like some magic condition. Wow, for now it seems like magic. We question ourselves whether this is real or surreal. Are we going to ever achieve the phase match in a real medium? It looks like it will not happen. Not for a isolated atom, atomic dipole, not in a material medium. Okay, but just wait. Maybe there is hope. We need, in order to build up some hope, we need to learn a little bit of what we would call crystal optics, right?